Hi, welcome to this video of acids and bases. So in this video, we're going to be talking about acid-base theories and basically how we can identify whether something is an acid and a base based on the theory behind it. And then we'll talk a little bit about the Bronsted-Lowry concept of the acids and bases a little more in depth. This also will tie in a little bit with our solutions unit because we'll talk about the behavior that acids have when we put them in water and write a little bit of those dissociation equations. All right, so let's get started. So there are some important things about acids and bases you do need to know. So some of those are just general properties of acids and bases. And we'll talk about some of these properties as the chapter goes on. But some things that are really important is in our everyday lives, like how could we observe or tell if something that we come across on a daily basis is an acid or a base? Some of that has to do a little bit with the feel of the substance or also the taste of the substance. Now, obviously, we're not going to eat or drink anything in lab, but a lot of the things that you come across on a daily basis that you eat, or some of them that you shouldn't eat, are acids and bases. So acids, all right, are typically going to be things that are sour. So lemon, like citric acid, lemons and oranges and things like that. So a lot of times, we're eating things like that and we just don't realize. So when you drink a Sprite, there's citric acid in it. So acids themselves are all going to have that sour taste. Now, obviously, I'm not going to give you some hydrochloric acid and say, go try this. So there are certain acids that are safe to consume and some that are not. Alkali is the term we use for bases. So when we use the term alkali, that means base or a base pH. So anytime you see that term, make sure you recognize that vocabulary word. And acids bases actually are going to have like a bitter taste. These are things that you probably normally would not eat. But you could think of something like chocolate or something like that bitter taste that you would get. But really, most of the time, your bases are going to be soaps or cleaning supplies, things like that. So obviously, we're not going to go eat soap because that would be disgusting and would also probably make us sick. They also have a feel to them. When you get a base on your hands, it has a very slippery feeling, kind of what you would call a soapy feeling, like all the soap didn't rinse off. That feeling is characteristic of the hydroxides in the water, okay? Acids are not going to have that feel. So an acid would feel just like natural water, but then obviously it's going to cause some irritation and sometimes worse. All right, so acid-base theories. There's some different types of acid-base theories or definitions. So the simplest definition is the Arrhenius definition. In the Arrhenius definition, we basically take an aqueous solution. So remember, aqueous means we put the acid in water. So exciting. And so we are talking about what happens when we put the acid in water. So this comes back to your basic understanding of solutions. If I take, let's say, HCl and I put that into water, right, what's going to end up happening? Well, the water is going to break apart those ions, and I'm going to have hydrogen ions in water that are aqueous, right? And I'm going to have chlorine ions in water that are aqueous. So an Arrhenius acid, in order to be an acid, would have to have hydrogen in it so that there are hydrogen ions floating in the water. With a base, if it's an Arrhenius base, it's going to donate hydroxide ions. So we would have something like sodium hydroxide, and we would put that in water, and the water molecules are going to attack it and break it apart, and we're going to have sodium ions that are aqueous and hydroxide ions that are aqueous. Remember, aqueous just means surrounded by water. So those polarity of the water molecules pull them apart. This definition is okay. It works for things that are very obviously an acid because they have hydrogens, or things that are very obviously a base because they have hydroxide. The problem is that it doesn't work for things that don't fit that. For example, NH3. NH3 we've talked about several times this year. That's ammonia. Ammonia doesn't have hydroxide, but ammonia is a base. So this is where the confusion comes in, because we have to determine, like, the basic Arrhenius definition of having hydrogen or hydroxide doesn't fit. When we put this in water, it does do something that creates hydroxide ions, but it's what it does to the water. So Bronsted-Lowry definition is actually a little better, because what it does is it talks about the donation of a proton instead of a hydrogen ion. So a proton is going to be similar to a hydrogen ion because it has a +1 charge and an overall mass of 1. But we're looking at its behavior in the water and what we end up with. So usually when we do a Bronsted-Lowry definition, we include the water, but we can also look at Bronsted-Lowry at how it behaves with other things that aren't water. So for example, if I have an acid, let's go with, I'm going to pick something that we know is an acid, but still I'll stick with HCl still. So if I take HCl and I put that into water, right, what we're going to see happen is when I put it in water, it's actually going to reach an equilibrium where the hydrogen ions are going to be donated to the water. So we would end up with H3O+, or that's just water piggybacking with a hydrogen ion, right? And since it gave the hydrogen from the HCl over, so this hydrogen went here, we end up with chlorine by itself. So it's still aqueous, but really we're showing kind of the same thing with the Arrhenius definition. The Bronsted-Lowry base is a little different. So let's say I take that ammonia, that was a little harder to tell that it was a base, and I put that into water. What it's going to do when it's in water, right, is it's going to accept a proton. So that means it's going to gain a hydrogen instead of losing. So overall, we're going to have ammonium ions. So that hydrogen is going to piggyback on top of that NH3, and then that's going to leave behind hydroxide from the water. So that's where those hydroxides are really coming from that contribute to it being a base. And then we've got that ammonium ion floating around. There's also the Lewis definition. And in the Lewis definition, really they're not going to test this on the AP exam. You don't really have to know it, but it is something you might see in college. So I'm going to go over it really quick, but we're not really going to talk about it much. A Lewis definition is when you accept an electron pair. So it's looking more at the molecular structures, right? So something that is considered an acid is usually deficient in electrons. So obviously hydrogens, right, are usually deficient in electrons, and so they're going to accept an electron pair. And then a base is going to be something that donates an electron pair. So an easy one would be like if I have hydrogen ions, right, those are deficient. And those are then going to, and I'm going to do it this way, I'm going to show, if I take the ammonia, if I look at the Lewis dot structure of ammonia, I've got this electron pair here, right? So these little dots right there, so that pair of electrons. And so really what it's doing is it's donating those to the hydrogen, right? And so that's how I know the difference. So ammonia has this extra pair of electrons that it could then donate to something that's deficient. And then the Lewis definition is something that is deficient can gain, which usually it's the hydrogen ion. So we're not really going to spend a lot of time on the Lewis definition. It just uses Lewis dots to explain that. This theory is going to explain all traditional acids and bases, and it has a host of coordination compounds, but we're not really going to get into coordination compounds. So we're going to ignore coordinate covalent bonds for right now because we don't really need to spend a lot of time on that. And we talked about it earlier in bonding. Okay, so let's talk more specific about the Bronsted-Lowry concept of the acids and bases. So when we look at the Bronsted-Lowry concept of acids and bases, and we're trying to use that as a way to identify or determine if something is an acid or a base, okay, one thing we need to understand is the concept of the conjugate acid-base pair. This is because really, even though we're drawing these as a one-way arrow, these are really systems in equilibrium. So we are going to kind of talk a little more about our equilibrium. So we're really going to do double arrows on these almost. Okay. And so we need to consider that these are reversible reactions, because as we proceed to the right, we eventually reach equilibrium. Then we could shift it back to the left if something happened and we needed to, whatever. But what we're really doing is we're looking at the substance that is present and what happens to it. Okay? So when we do that, I think I have a typo here. I think this is supposed to be water here. That's H2O. My bad. We're looking at the reactants and the products that are provided in the reaction to decide what happens. So if I have HNO3 and I put that into water, what we're really doing, and I'm going to make this a little bigger so we can see it a little better. What we're really doing, okay, is we're looking at this substance and what happens to the water. So water, H2O, becomes H3O+. That means this hydrogen added a hydrogen over here to make that. So this is donating, so that makes it an acid. And the water is actually receiving because it's amphoteric. It can do either or. It can give away a hydrogen, or the proton, right? Or it can accept it. So in this case, the water's accepting it, which makes it the base. So then on the other side, right, then the H3O+ would be a conjugate acid. Because if the reverse direction or reaction happens, water would then give away, right, the hydrogen to the NO3. The NO3 would be a conjugate base because it has the ability to accept that hydrogen ion or that proton. So this is a neutral compound that is an acid, okay? We can also have a cation as an acid, but the exact same thing is going to happen. We look at the cation. We look at our water, and we look at what happened to the water on the other side. When we look at that substance, right, or we look at the NH4, and we look at what it became, it goes from 4 hydrogens to 3 hydrogens. One of these hydrogens is going to the water, so that makes that an acid. Therefore, water is accepting the proton, and it's a base, right? Same scenario with an anion. That would be our negative ion. Same look, we're looking at H2PO4 in our water. When I look at H2PO4, all of a sudden we go down a hydrogen. And look, our water went up a hydrogen. So one of these hydrogens is going to go over here. So this is an acid. This becomes a base. Now, I'd like to point out, it doesn't have to be written acid-base. You can flip them, and base could be first and acid could be second, whatever. You can write your reactants and products in any order. But the donation of the hydrogen ion and the acceptance of the hydrogen ion are not going to change. Okay? So when we look at our conjugates, the conjugate pair, then we would look at the system in equilibrium, right? So in equilibrium, on the product side of this middle equation, the H3O+ would be a conjugate acid, and the ammonia, which we talked about earlier, is a base, so that would be the conjugate base of the ammonium. Same thing here, H3O+. Hopefully you're seeing a trend here. H3O+ is always going to be conjugate acid. Always, 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 okay? And HPO4 would then be a conjugate base. So if you see H3O+, that's essentially hydrogen floating around. It is an acid, okay? So very easy. So in this case, notice, let me make it a little smaller. It says the formation of H3O+. This species is called a hydronium ion. So you can call it a hydrogen ion, but specifically, this is hydrogen, right? So kind of showing you the picture of what's going on here. So we've got our water, and then what we see is this hydrogen then adds to it. So you end up with this extra hydrogen ion floating around on there, right? And so when we look at this whole complex, here's the water still with the hydrogen attached to it, that hydrogen ion attached to it. That's the hydronium ion. That's what that is. And so a lot of times we'll omit the water and just say like H Cl becomes H plus and Cl minus, because we know that the only way the H plus could move away is to be attached to the water. But yeah, so anytime you see that you made H3O plus, you know this solution is acidic. Very important. H3O plus is acid. Okay. We can also have bases, and so we talked about these already. So like, for example, the ammonia, if I have NH3 and it becomes NH4 plus, right? So in this scenario, NH3 is gaining, right? So that means the water is giving away. So notice how the arrow switched here. The water is giving this, so this becomes the base because it gave the hydrogen away. And then water becomes hydroxide, so that becomes the acid. So on our other side, our conjugate would be the ammonium would be a conjugate acid because it has extra hydrogen. It could give that away, right? And the hydroxide, of course, is going to be a conjugate base. If I look at something that is an anion or negative ion, I think this is supposed to say cation. Nope, it is anion, just kidding. I'm looking at something that's an anion. Same scenario, this is hydrogen deficient, so the only thing it could do is gain a hydrogen, right? It can't do anything else, can't give one away. So it's going to gain, and so that would be that would be just a base, and then the water is acting as an acid. I don't know why I keep trying to write a conjugate, but it's an acid. On my product side, the HCO3 would be a conjugate acid because it could then donate that hydrogen over, and then this would be a conjugate base because it's hydroxide. So hopefully you're starting to see again that trend. H3O plus tells us an acid. Hydroxide means base. So we're going back a little bit to that Arrhenius definition as well. But we're looking more at what's happening in the reactions. So phosphate in this scenario, right, would have be hydrogen deficient. So that means one of the hydrogens is going to come from the water. That's going to make it a base because it's accepting. And then the water is going to be giving away and making hydroxide, so that's an acid. So then we look at our products, we've got the conjugate acid here, and then of course hydroxide conjugate base. All right, so in this case, again, formation of hydroxide, right? It's always going to be a base, so if we see hydroxides made during that reaction, then that's going to be a huge indicator that that is a base, and that this substance is going, whatever the main substance is that we put in water, is a base. So that helps us recognize that or see that part. All right, so in this exercise, 1, I want you to identify the acid on the left and its conjugate base on the right, and then identify the base on the left and its conjugate acid on the right. So you're just basically doing the same thing we just did, right, and telling me. And then in B, what's the conjugate base of H2S? And then C, what is the conjugate acid of NO3 minus? So you need to do these and submit these in your notes so that I can see that they're done, okay? All right, one other really important thing, that acids are only going to donate 1 proton at a time. So things that have more than one acid take multiple steps and multiple waters for that acid to be donated. So, or those hydrogens to be donated. So let's look at an example. We can have an easy monoprotic acid, which are mono means one acid, right, or one hydrogen. That would be like acetic acid. So if I take acetic acid, it's an acid, so I know for sure that when I put that in water, right, it's going to donate the hydrogen over. And so I'm going to draw equilibrium arrows really on these, okay? And so I know it's going to give away, and so I'm going to end up with H3O plus. And then the acetate ion is going to be floating around in the solution. Remember that this is going to be aqueous. We don't ever have ions that exist alone, and we always include our units on those, or our charges on those. So that's pretty easy, because then now the acetic acid, that acetate ion isn't going to keep losing those hydrogens because that's a covalent compound in that polyatomic ion. The diprotic acids are acids that have 2 hydrogen ions, right? So they have 2. Well, the thing is they can't lose 2 at once. So it would be 2 steps. So your first step, right, would be, in this case, oxalic. This is oxalic acid. So H2 C2O4. And we add that to water, and we've got our normal, what we would think, right? One of those hydrogens goes to the water, and we end up with H3O plus. And now we have a hydrogen, only one of those initial hydrogens left with the oxalate ion. And my charge becomes a -1. So notice my charge was neutral. I lost one hydrogen ion, and it went down to negative. This still has a hydrogen to lose. So it could go through a second step. Now I would like to point out that second step is not as likely to occur. It becomes less soluble as we remove hydrogen ions, but it could still happen. So this HC2O4 ion in water could still lose that additional hydrogen. So then we make another H3O plus when this happens. And we're left with the oxalate ion all by itself with a -2 charge. So we started with a -1, and now we lost another hydrogen, and we went to a -2 charge. All right. So not too hard, right? If it was polyprotic. So polyprotic can be donating as many hydrogens as it has, which means lots of hydrogens. So a good example of this one, of course, is phosphoric acid, because phosphoric acid has 3. So in this scenario, your first step would be H3PO4, and we put that in water, right? And what do we see happen? Well, hopefully you're realizing that's neutral. We're going to lose the hydrogen and make hydrogen ions. And then, oh my gosh, my H3 becomes H2PO4, right? And so that's going to be a minus charge. This could then, again, less likely, but could still lose another hydrogen. So H2PO4 could be at minus, can be attacked by another water. And when that happens, again, we end up with H3O plus. And now one of those hydrogens went to the water. So now we end up with HPO4 minus 2. Notice, -1, we lost another hydrogen, we went -2. Still have hydrogens that could be lost. So there could be a third step here. HPO4, -2, and water. When it loses that other hydrogen, ends up making, again, another H3O plus. And PO4, and what do you think the charge is going to be? We were at -2, we lose one, -3. Phosphate's charge is -3, so that should work out. So at the end, we would have not very much PO4 minus 3, because really what's going to happen is this is going to happen less and less and less as we work our way through. So the first step is very likely to happen, but then the second and the third step are going to become less likely to happen. So basically it becomes a weaker, and we'll talk a little bit about weakness and strength the next video, but it becomes a little bit weaker as you go down. Polyprotic bases are going to be the same thing. Those are going to be ones that accept more than one hydrogen ion, so it would be walking your way backwards. So those are going to be anions that have -1s, -3 charges, things like that, so that they can take them on. So it would be kind of like looking at it backwards, if you were kind of considering that. We can also have compounds that are what we call amphiprotic or amphoteric. I see amphoteric a lot more than protic, but it just kind of depends on what your professor says and who you have and all those things. But these are going to be molecules or ions that can behave as either acids or bases. So that means that they can accept or donate hydrogens. So for example, in the example above, water, very perfect example, right? Because water can accept a hydrogen ion and make H3O plus, right? Or water can lose a hydrogen, right? I'm going to say minus a hydrogen, minus an H plus, and then it makes the hydroxide. Remember, we don't really normally use the minuses, but I'm just showing you that, we can lose it or we can gain it. And we get multiple options with that. So we can accept or we can lose. But several of these other compounds would also work that, especially when you look at these polyprotic and diprotic acids. So for example, this PO4 minus 3, or not PO4 minus 3, HPO4 minus 2, right? It could lose, but it could also gain because it's got the hydrogen, but it's not really stable as HPO4 negative 2. So it could gain a hydrogen, right, which would make it act as a base, but it could lose it and go to the phosphate. So those are options that we have. Those are called amphoteric. Most common, obviously, amphoteric is water, though. Okay, so here is an acid dissociation or ionization reactions, just practicing writing the dissociation of each of the following of the acid. So we're going to treat each of these as if they are an acid. Okay, and when you treat them like they're an acid, you're going to donate, right, the hydrogen from them. So write the simple dissociation, ionization, omitting water for each of the following. You can put the water in there if you want. I don't care either way. Okay. So I say it says omitting water, but really I like to write the water in there because I like it to see H3O+. But that's all you're doing is you're working through. When you get down here to these ones, I don't want you to freak out. These are what we call complex ions. Okay. And we're actually going to ignore this one because that's something you don't need to know. But when we get down here to the aniline, I can never say it right, ion, the C6H5 stays together. You're going to lose your hydrogens from the H3. That's right there on the end, like ammonia, right? So that can kind of help you out. But you should be able to do those. They're not that hard, okay? So A, B, C, D, you're basically treating them as if they are acids, and you're writing an acid dissociation equation. Should be pretty easy. Let me know if you have questions, but those need to be included in your answers that you submit for your work. I appreciate it.